Hey learners, Jared here. So I wanted to walk through on our homework question 39, part B, where we're looking for what maximum speed our iPad, our iPad could have, our vehicle could have in order to just miss the deer. So instead of our V initial being 19 or 20 or whatever it was that your problem said, our initial velocity is going to be our unknown. So our initial velocity, Vx initial, that's what we're going to be trying to figure out. But we still have the same kind of parameters that we have before. So we still have this initial phase where our displacement is linear, and that distance now, delta x, I'm going to call it delta xr for the reaction time. So that displacement right there, and then this displacement right here. So this distance that we go, delta xb for braking, those two distances added together need to give us 35. So the deer is still 35 meters away, and we still have these two displacements that we don't know because we don't know what velocity we started with. That's going to be our unknown. So let's start with a kinematic, and I'm going to start with, I've got a position versus time graph here, so I'm going to start with the position versus time graph kinematic right here in blue. So x is x initial plus vx initial t plus 1/2, and then our acceleration times time squared. And so this kinematic applies to both sections. It applies to the reaction time and it applies to the braking time. And what I'm going to do first is I'm going to subtract x initial over to the other side. So we would end up with something that looks like this. X final minus x initial is equal to vx initial t plus 1/2 ax t squared. And that x final minus x initial right here, that is the same thing as delta x. And so what I'm going to do is utilize this kinematic right here for both sections. Everywhere that we have a different acceleration, we have a different kinematic. So I'm going to use that for here. So delta x reaction is equal to Vx initial, which is our unknown, plus, times t, plus 1/2 ax t squared. And I'm going to do the same thing for our braking phase. So delta x braking is equal to Vx initial. It's the same velocity, plus 1/2 ax t squared. And we don't know time, but what is the same between both of those is that initial x velocity. But the kicker here is that I don't know Vx initial, which means I can't know the displacement. I do know how long the time is for that reaction phase. I also know that the acceleration is 0 during that reaction phase, but we don't know, we have two unknowns here. And it's even worse with the braking phase because I don't know how far I go when I'm braking. I don't know, oops, I forgot my time right here, times t. I don't know the initial velocity. I don't know the time. And so I have three unknowns in that kinematic. And so this is where you get to a point where, okay, this kinematic isn't working because I just have too many unknowns. Is there a kinematic I could use that has less unknowns? And the answer is yeah. The kinematic where we don't have the time component. So what we could do is utilize the fact that this kinematic right here, whoops, v x squared, our final velocity is equal to our initial velocity squared plus 2 times our acceleration, and then times delta x. And for the braking phase, I know that my final velocity is 0, so I can just cross that off. And now I've got an equation where, yeah, we don't know our initial velocity here, and I don't know that delta x braking, but it's this Vx initial and this delta x braking that we're going to use, two equations, two unknowns. And I'm going to do the same thing for my reaction phase. So for the reaction phase, I know how much time I've got, and I've got the same two unknowns over here. Delta x, or the same unknown right here, delta x, or Vx initial. And so we can kind of bridge the gap here by also knowing that those two displacements added together is equal to 35 meters. And so we've got let me highlight these. I've got 1, 2, 3 unknowns, and now I've got that's a highlighter. I've got 1, 2, and then 3 equations. And what I would do, Vx is what we're trying to figure out. And so what I would do is I would substitute that last. And so over here with equation 1, what I'm going to do is I'm going to get delta x r equals. So I'm going to subtract over delta x braking. So I'd end up with something that looks like this. Delta x r is equal to 35 meters minus delta x braking. And I'm going to take that and I'm going to plug it in to this equation right here. And so I'd end up with 35 meters minus delta x braking is equal to Vx initial, which is our unknown, that's what we're trying to figure out, times t, and that's the reaction time, which is half a second. And so the unknown that I want is right here. I want to know Vx initial. And so what I'm going to do is solve for it last. So this equation right here, I'm going to solve for delta x braking. So I'm going to add it over to the other side, and I'm going to subtract the Vx initial over to that 35. So 35 meters minus Vx initial times 0.5 seconds is equal to, I would have added delta x braking to the other side. And so now this, we can make our final substitution, and I can solve for Vx initial. So 0 equals Vx initial squared plus 2 times our acceleration, which we know to be negative 10, and then times delta xb, which is all of that over there. So it's 35 meters minus 0.5 seconds times Vx initial. And so now I just have one equation and one unknown. So we'll need to distribute that negative 20 . And so if I do that, we would end up with, what do I have? 10 times 35 is 350 times 2, so minus 750. And then negative 20 times negative 0.5 is going to be plus 10 Vx initial. And so now I've got this, Whoops, I wrote that initial way up high, didn't I? That is going to have to be solved using a quadratic. So on your calculator, you could go y1 equals, and our a coefficient is just 1, so you'd go y equals x squared plus 10x minus 750. And we're looking for where that is 0. So I know that's a lot of math, but the important thing is that we try to kinematic, hit a snag, and then try a different kinematic. That's kind of the main goal for this type of problem, is to get you used to kind of getting stuck with one kinematic and then being able to pivot to another.